Hello dear students, today we will discuss the next point in the quantum free electron theory, that is Fermi energy. So this Fermi energy concept is introduced in the quantum free electron theory. So according to quantum free electron theory, free electron energies are quantized. This we have discussed in the postulates. Thus, if there are n free electrons, if there are n number of free electrons, there exist n closely spaced energy levels. Since electrons are distributed among these energy levels according to Pauli's exclusion principle. So in the PUC you have studied Pauli exclusion principle, which states at absolute zero temperature, two electrons with least energy having opposite spin occupy lowest available energy level. The next two electrons with opposite spin occupy next energy levels, and so on. In this way, these n free electrons occupy n naught energy levels and remaining n divided by 2 energy levels are vacant. So the most energy levels occupied at absolute zero temperature is called Fermi level. This energy corresponding to that level is called Fermi energy. So in the figure you can see there are different energy levels. If you consider n number of energy levels, according to Pauli's exclusive principle, two electrons with opposite spin will occupy each energy level. So there will be n divided by 2 energy levels which are going to be occupied, and n divided by 2 energy levels which will be free. So these are vacant energy levels, these are filled energy levels. And this topmost collection of energy levels is called Fermi level, and the corresponding energy is called as Fermi energy, and that's what we are going to define here. The Fermi energy is defined as energy of that energy level below which all energy levels are completely occupied and above which all energy levels completely empty, and it is denoted by EF. So this is about the Fermi energy concept. Now we will go for the Fermi factor concept, which is again dependent on the Fermi energy. We know that at T is equals to 0 Kelvin, all energy levels below Fermi energy are filled. So this is the Fermi energy level. All the below energy levels are filled, and all energy levels above Fermi energy are empty. So above Fermi energy level, all the energy levels are empty. But as temperature is increased, now this is the condition at absolute zero temperature, that is 0 Kelvin. But as the temperature is increased, some of the electrons absorb energy and start migrating to energy levels above EF. So this is the condition at 0 Kelvin. When the temperature is increased, the electrons which are present close to Fermi level, they will absorb the energy and they will be shifted to the higher energy states. As a result, there some vacant energy levels below Fermi energy and filled energy levels above Fermi energy. Now it becomes difficult to say whether a particular energy level is occupied or vacant. So the probability of occupation of any energy level is given by a mathematical function. So dear students, this is the condition for 0 Kelvin, but as the temperature is increased, the electrons which are present close to Fermi level, they will absorb the energy and they will be shifted to the excited state. So there will be some energy levels which remain vacant below Fermi energy, and there are some energy levels which are going to be filled above Fermi energy. but we will not come to know which energy is free and which energy level is occupied, and that is given by a probability of occupation of any energy level. It is given by a mathematical function which is called as Fermi factor, and that Fermi factor is given as f of E is equals to 1 divided by e to the power of E minus Ef divided by kT plus 1, where f of E is called Fermi factor. Now how to define this Fermi factor? Fermi factor is a function which gives the probability of occupation of an energy level E at a given temperature T for a material in thermal equilibrium. So using this probability factor, we can find out the occupation of any energy level E at any given temperature T, and it is for any given material at thermal equilibrium. So this is the Fermi factor. Now we will discuss the variation of effect of temperature on Fermi factor. So this is the probability function which I said it is a Fermi factor. Now how this Fermi factor is dependent on the temperature, so that we will discuss in the three different cases. So the first case, if you consider case 1, at absolute temperature, that is T is equals to 0 Kelvin, and energy less than Fermi energy. So we are considering the energy levels less than Fermi energy level. So substituting these conditions in the above Fermi factor equation, we get, so substituting T is equals to 0 and E is less than Ef. So in this above equation, it is going to be f of E is equals to 1 divided by this one, here it is written as it is 1 plus e to the power of minus infinity. When we simplify this term, we will be getting e to the power of minus infinity. Since we know that e to the power of minus infinity is 0, so we will be getting f of E is equals to 1 divided by 1, that is equals to 1. Now what it means that f of E is equals to 1? The distribution function f of E is equals to 1 means all the energy levels below Fermi energy are fully occupied. There is 100% probability of finding an electron below Fermi energy level. So probability function 1 means you will definitely find electrons in the energy level below Fermi energy at 0 Kelvin. Now what is the second case? The second case we will take at absolute temperature T is equals to 0 and energy level greater than Fermi energy. Substituting this condition in above Fermi factor equation, we get, in the first condition we have taken energy level less than Fermi energy, and here we are taking energy level greater than Fermi energy. So when we substitute T is equals to 0 again, f of E is equals to 1 divided by 1 plus e to the power of infinity, that is 1 divided by 1 plus infinity, that is 1 divided by infinity, that is equals to 0. This indicates that at T is equals to 0 Kelvin, energy levels above Fermi level Ef is not occupied. So the probability function f of E is 0, which means there is no probability of finding the electrons in the energy level above the Fermi level. So it is not occupied by electron, that is they are vacant. So the energy levels above Fermi energy are vacant here. Now we will go for the case 3. Now what is the case 3? Case 3 is at temperature slightly above 0 Kelvin. In the previous two cases we have taken temperature as 0 Kelvin, but here we are taking temperature greater than 0 Kelvin, and we are taking the energy level which is exactly equal to Fermi level. So substituting this condition in the above Fermi factor equation, we will be getting f of E is equals to 1 divided by 1 plus e to the power 0. This is equals to 1 divided by 1 plus 1, or 1 divided by 2, this is equals to 0.5. So what does it mean? It means that at temperature above 0 Kelvin, that is at room temperature, and at energy level equals to Fermi energy, there is only 50% probability for an electron to occupy Fermi energy level. Now why this is the case? As we have already discussed in the probability factor, when you increase the temperature, electrons will absorb the energy and they will get shifted to the higher energy levels. So the probability is 50-50. Only 50% of probability will be there if you go on increasing the temperature. That is, you may get an electron in the Fermi energy, or you may not get the electron in the Fermi energy level. So this is how we will discuss the effect of temperature on Fermi factor. Thank you.